Let's do another example of finding the singular values of a matrix. And so here we have a matrix that isn't square, and so we will have to make a choice as to what path we want to take. Now, how do we find the singular values of a matrix? So, the first step here is to construct the matrix DH times D, where H denotes the conjugate transpose. In our case, this is a matrix with real entries, and so the conjugate transpose is the same as a transpose, but I will leave it as DH for now. Or we can do the matrix D, DH. Which one are we going to want to do? Well, I will answer that question as we go further, but the second step here is once we construct these matrices, or one of these matrices, we want to find then the eigenvalues of D of DHD or of D DH. And then once we find the eigenvalues, let's call these eigenvalues lambda I. Once we have found these eigenvalues, we want to find our singular values. So the singular values sigma I, these are simply equal to lambda I like this for every lambda I bigger than 0. Okay, so let's get started. The first step is to construct either DH or DDH. I will do both in order to illustrate which matrix we would want to take. Because since this matrix is not a square matrix, whatever choice we make here will alter how easy it is to do the rest of these calculations in general. We will see for this case that we could go either way and the calculations would be pretty much the same. But let us start with DHD on this side, and we'll do DH on this side. Okay, starting with DHD, let's take the transpose of this matrix. So this is 2, 0, 0, 3, 0, 0. And the transpose multiplies our original matrix, 2, 0, 0, 0, 3, 0. Okay. Let me scroll down. If we do the matrix multiplication row by column, this gives us 4 and 0 and 0, and then 0, 9, 0, 0, 0, 0. Okay, so we have a 3 by 3 matrix. How about, in this case, D, DH? Okay, so D here is 2, 0, 0, 0, 3, 0. That's our matrix D, and then we take its transpose, and then we compute using matrix multiplication. What does this give us? It gives us 4, 0, 0, 9. Okay, well, we see in this case that, okay, well, we've done our first step here. Boom. Okay, now looking at these two matrices, we can see, oh, they're both pretty simple matrices. In fact, they're pretty similar except for this row and column here, these extra zeros. But in general, that's not always the case. We won't have diagonal matrices that look so similar. And generally, when we want to attack the second step, when we want to find the eigenvalues of the matrix we constructed, well, over here we need to calculate the determinant of either of these matrices, of the one which we chose. But calculating the determinant of a 3 by 3 matrix is a lot more complicated than calculating the determinant of a 2 by 2 matrix. And so in general, we would want to find the smaller matrix. That would ease up our calculations. In general. But in our case, both these matrices are fairly similar, and in fact, it's immediately apparent what the eigenvalues of these matrices are. And the reason why that's apparent is because these are both triangular matrices, or more particularly, they are diagonal matrices. So they're both upper and lower triangular, which means they only have entries on the principal diagonal. And we know that the entries on the principal diagonal are in fact equal to our eigenvalues. So we can immediately say lambda 1 is equal to 4, and lambda 2 is equal to 9. So we have found our eigenvalues of this matrix. Check. Now let's find the singular values. Well, the singular values is our third step. This was our second step. The singular values are pretty simple. These are both bigger than 0. This being a 0. And so this is just equal to the square root of 4, which is 2. And then the one corresponding to our lambda 2, sigma 2, is the square root of 9 equal to 3. And so this is the singular values of our matrix.